My dear friends, you're welcome once again to another fascinating math video. Now in this video, we shall be taking problem from mathematical induction. Mathematical induction is a very important aspect of maths. Will I call it an aspect of maths? No, it's not a branch of maths anyway. But when dealing with analysis, specifically talking about the sequence and series, when looking at sequence and series specifically, mathematical induction is a very useful tool. Also, when it comes to number theory, because the number theory is built on the set of positive integers, mathematical induction is also a useful tool. It's a method that is used to provide proof for statements or propositions. In mathematics, when propositions are made, we don't just accept them like that. They have to be proven. You cannot make claim as to such as such is without any proper foundation or proper provision of basis upon which your claim stands. For you to say this is it, there must be a process, there must be a foundation, a basis upon which that claim is made. And when we make claims in mathematics, we make claims on theorems, definitions, axioms, previously proved theorems. All right. For any of your proposition to be accepted, to be universally accepted, it must be laid on a proper mathematical foundation. All right. Of which mathematical induction is one of the methods used to establish a claim. I would like to still add that I render a private or group personal online group or stroke private online mathematical tutoring service. I also assist in assignments and tests and also projects and research work. So if you are in need of these services, any of these services I've mentioned to you, be very free to get across to me, message me directly so we can organize a class or we make plan of how the class should be organized. All right. So it's a time whereby you can discuss with me one-on-one because in this time around we are doing the class remotely in the sense that we discuss via systems. All right, provided you have the necessary equipment such as your laptop or your tab, your writing pen, we are good to go. Be very free to get across to me and I will make sure that the class is so interesting because I have an ample experience on teaching spanning over a decade now. So be very free to get across to me if you're in need of such a service. So let's quickly go into the solution of these problems before us. Over here, we are told to show that the statements hold for all positive integers n. So take note, mathematical induction is a method that is applied strictly to positive integer. You can't use it when talking about the real number in general. It's restricted to positive integer. Hence, I said it's very applicable when it comes to the analysis. And under analysis, we're talking about the sequence and series. Very, very applicable. All right, because the domain of a sequence and series are the set of positive integers. Sometimes they include set of non-negative integers sometimes, but in most cases, the domain is strictly the set of positive integer. Then number theory, that is a very important aspect that mathematical induction can be applied. All right, so it is very good to get the knowledge and what it's all about. Now, before I solve this problem, let's make the axiom of induction. Let me provide the axiom of induction so you get what I'm talking about. Now, firstly, I will discuss on the axiom of induction. Now, let S be a set of positive integers. All right. This is not a solution. I'm only teaching briefly here. Positive integer. Then, if number one is an element of S. All right. Then number two, K is an element of S implies K plus 1 is an element of S. Then N will be an element of S. All right, for all N that are in the set of the positive integers. So this is just the axiom upon which mathematical induction is built. All right. It states that 1 should be an element of the set, because this set, we have to prove that this set will contain all positive integers. So for that to happen, first of all, we prove that 1 is an element of the set. Then 2, that if k is an element of the set, that will imply that k plus 1 is an element of the set. So if these two conditions can be established with certainty, then we can boldly say that n is an element of the set S, where n is any positive integer. In other words, S is the set of all positive integers. So that is how that is a foundation upon which mathematical induction is built. It's built upon this axiom. We call it the axiom of induction. All right. You can think of this axiom as the domino theory, whereby if you push the first domino, it will fall. And if any domino fall, it will cause the next to fall. So in that case, all the dominoes will fall, will each fall, all right? So it's likely to be that. So with this brief explanation, we can go over to solving the problems above, all right? I don't intend giving detailed discussion because this is solving problems. We are interested in solving past questions and not giving detailed teaching, all right? So let's look at the solution of these problems I've given above with this idea. Now, the first, we have to show that number 1 to the power 3. Let me write it down. Number 1 to the power 3 plus 2 to the power 3 plus and so on to n minus 1 to the power 3 is less than 1 over 4 n to the power 4, and that is less than 1 to the power 3 plus 2 to the power 3 plus dot 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 plus n to the power 3. All right, so we have to show that this is true for all positive integers. All right, so we can say let S be the set of, let me remove this, of all positive integers for which 1 to the power 3 plus 2 to the power 3 plus dot 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 to n minus 1 to the power 3 is less than 1 over 4 to the power n to the power 4, less than 1 to the power 3 plus 2 to the power 3 plus dot 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 plus n to the power 3. All right, we can say this. We can say this. Now, if you observe carefully, this is a combined inequality. All right, this is a combined inequality. So we can take each inequality separately for simplicity reasons. All right. So if we take each inequality separately, so let me write that first. Taking each inequality separately. All right. We can do it straightforward, but I want it to be easy for every one of us that will come across the video. All right. So it is best we take them separately and later do combination separately. So we can say let S sub 1 be the set for set of, before I put that for, let me put of first, set of all positive integers for which 1 to the power 3 plus 2 to the power 3 plus dot 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 plus n minus 1 to the power 3 is less than 1 over 4 n to the power 4. All right, let's say this. We are taking each inequality separately. We are going to the other part, but let's deal with this part first. So S sub 1 is there. All right, now observe carefully. Observe that if we put 1 here, 1 minus 1 to the power 3, and that will be less than 1 over 4, 1 to the power 4. All right, this is not true. It's true, because 1 minus 1 is 0, 0 to the power 3 is 0, and it is true that 0 is less than 1 over 4. So since that is the case, and we have already defined our x sub 1, that is this we've defined over here, look at it. we've already defined S sub 1 to be the set of all positive integers for which this statement you see over here is true. Since S sub 1 is such a set, and we have established that this holds, it means that 1 must be in S sub 1 because we said initially that S sub 1 should be the set of all positive integers for which the statement is holds. All right? And on substituting 1 in, it will make the statement to be true because it is true. So in this particular case, we can say 1 is an element of the set S sub 1. So I can write, hence, 1 belongs to the set S sub 1. Can you see what I'm doing? Now the next thing, we suppose that there is a k. Now we can say suppose that k is an element of S sub 1. Now if k is an element of S sub 1, we are saying indirectly that the statement we hold when we assume an arbitrary integer k, all right, positive integer k. We are saying that the statement will hold. That is, this statement I have written here can be equally interpreted as 1 to the power 3 plus 2 to the power 3 plus dot 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 plus k minus 1 to the power 3 less than 1 over 4 k to the power 4. That is why saying that there is a positive integer in the set S of 1 for which the statement will still hold. That is the assumption stage. All right. Now, what we do, we try to use this assumption stage to establish that the statement will hold for a number k plus 1. All right. So if we can use this assumption to establish that the statement holds true for a number k plus 1, in so doing, we have by the axiom of induction, it follows that the statement will hold for all positive integers. All right. So let's use this assumption. Let me call it star for example. We shall use this to establish that the statement will still hold true for a positive integer k plus 1. All right. So for that, we say consider the expression. Consider the expression 1 to the power 3 plus 2 to the power 3 plus dot 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 plus k minus 1 to the power 3, then plus we can put this and write k plus 1 minus 1 to the power 3. And that will give us 1 to the power 3 plus 2 to the power 3 plus dot 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 plus k minus 1 to the power 3 plus. Now, on simplifying this this term in the square parentheses, we have just k to the power 3. All right. And also, this can be written as, you can put into parentheses as 1 to the power 3 plus 2 to the power 3 plus dot 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 plus k minus 1 to the power of 3. Then close the brackets plus k to the power 3. All right, we can do this. Now, looking at star, we see that the expression here is exactly what is in the left-hand side of star. So because of that, we can form this inequality. We can write from star. Now we have, therefore we have 1 to the power 3 plus 2 to the power 3 plus dot 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 plus k minus 1 to the power 3. All right, that is star. Then plus k to the power 3. That should be less than 1 over 4 k to the power 4 plus k to the power 3. That is, we are adding k to the power 3 to both side of star, to both sides of star. All right, we are adding k to the power 3 to both sides, and if we do that, we shall have this current line we are in now. So we are almost there. Now, this you see, note, observe, let me write this, observe that 1 over 4 to the 4k to the power 4 plus k to the power 3 can equally be written as k to the power 4 plus 4k to the power 3 over 4, right? That is your usual fraction manipulation. Now, let's look at something very, very important. Very, very important. Now, look at this. Consider the expression. Consider the expression. What is it? Let's look at k plus 1 all to the power 4 divided by 4. Let's look at this expression and compare this expression with this over here to see which is greater. All right. My page is exhausted, so let me take in more page so we can continue the work. Now, this can be written, now k plus 1 to the power 4 over 4 can be written as, you can bring out your 1 over 4 and expand this binomial, k plus 1 to the power 4. So on expanding, we shall have k to the power 4 plus 4 combine 1, k to the power 3, plus 4 combine 2, k to the power 2, plus 4 combine 3, k, then plus 1 to the power 4, which is 1, all right? So we have this expression at hand. Now look very carefully, Now this can be equally written as 1 over 4, k to the power 4, plus, now 4 combined 1 is 4. So we have 4k to the power 3, then plus 4 combined 2 will give us 6k squared, plus 4 combined 3 is still 4k, then plus 1. Now this can be further written, sorry for that. This can be further written as, we can write this as k to the power 4 plus 4k to the power 3 all divided by 4 plus 6k to the power squared, that is the power 2, plus 4k plus 1 all divided by 4. Now you can see that this expression here is exactly what you are seeing this way. Can you see that? Hope you can see that clearly, which is what you are still seeing here. Is it? Look at it here. Can you see that? So from this line we are seeing here, we can write the inequality as follows. That means that k plus 1, therefore k plus 1 to the power 4 over 4 is bigger than k to the power 4 plus 4k to the power 3 over 4. And by what amount? By this amount. It's bigger by this amount, all right? So in that case, that inequality I was telling you about, I mean this over here, can now be rewritten as, we can say, therefore, 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k minus 1 to the power 3 plus k to the power 3 is bigger. Is it bigger we saw there? Yeah. Is it bigger? Oh, less. It's less. It's less than 1 over 4k to the power 3 plus 4 rather plus k to the power 3. And this we have proven that this is less than, at least look at it here. Can you see this? We've just proven that that is less than k plus 1, and we can write 1 over 4 here, all to the power 4. So by the transitivity property of inequality, this can be written as 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k minus 1 to the power 3 plus k to the power 3 strictly less than 1 over 4 multiply k plus 1 to the power 4. So we can have this statement very, very correct. So what are we saying? We are saying that the assumption of this statement over here, which is in star here, this assumption you are seeing here, has implied this statement. Can you see that? So we can say, therefore, 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k minus 1 to the power 3, which is less than 1 over 4k to the power 3. I'm talking from star now. From star, look at star over here. Hope you can see that. Look at star. I mean this, all right? This. So for this, our assumption stage have implied that 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k minus 1 to the power 3 plus k to the power 3 is less than 1 over 4 k plus 1 to the power 4. So this is 4, sorry, this is not 3. I mean this here, this is 4. All right, okay. So now that means, in other words, if you want to say this in another way, that is k being an element of S sub 1 has implied the statement that k plus 1 is also an element of S sub 1. And by the axiom of induction, we can say therefore n is an element of S sub 1 also for all n that are elements of the positive integers. All right. So we've established that this statement is true. That is, I mean, this portion we took out separately. I mean, this portion here. We've shown that this portion is true for all positive integer. In other words, S sub 1, which is this set you are seeing, we've shown that S sub 1 contains all positive integer. That is, the statement is true for all positive integer. So we've proven that part already. And the next part we want to establish is this part, because don't forget we said taking each inequality separately. We said that initially in passing, we said it, all right? So we've looked at this part already, the first part of the inequality. So let's take the second part of the inequality. So we can go and say also let S sub 2 be the set of all positive integers for which the statement 1 over 4 n to the power 4 is less than what is written there. Let's see what is written there. Okay, that is 1 to the power 3 to n to the power 3. For which 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 dot 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 to n to the power 3. Let S sub 2 be a set of all positive integers for which this statement will hold. So we want to claim that the set S sub 2 contains all positive integer also, as we did for S sub 1. All right, in the first part of the first inequality we considered. So let's look at this now. We can write this statement. This is equivalently written as 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus n to the power 3. That is bigger than 1 over 4 n to the power 4. We would have worked from this part, but I don't want it to prove difficult. So let's go by this way. This way will prove very easy. All right. Now let us prove that this statement holds for all positive integers. In other words, that S sub 2 is a set of all positive integer. Look at the way we define S sub 2. We define it as the set of all positive integers for which the statement we hold. That is how we define it. So we want to show that S sub 2 is indeed a set of all positive integers. I mean, all natural numbers. All right. So how do we go about it? Let's test whether one is in the set S sub 2. Let's test. How do we test? On taking one term, we have that 1 to the power 3 is bigger than 1 over 4, 1 to the power 4. All right. Since this is true, it means that 1 is an element of the set S sub 2. All right. So the next stage is to suppose that there is a k in S sub 2. In other words, we have to suppose that the statement holds true for a positive integer k. All right, so we can say suppose k is an element of S sub 2. You see that we suppose that is a supposition stage. So by this in other words, we want to write it in statement form. We can say that is 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k this time around, because we are supposing that the power 3 is bigger than 1 over 4 k to the power 4. We are supposing that, all right? So take note of what we are doing. Then let's consider the expression. We can say consider the expression. Consider the expression. Let's consider 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k to the power 3 plus k plus 1 to the power 3. Let's consider this expression, all right? Now, this expression you see here can be written as 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k to the power 3. We can put this into parentheses. then plus k plus 1 to the power 3. Now, from this, our supposition, let me call this star, all right? From this, our supposition, we can fashion the inequality. We can write this as 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k to the power 3. Then we think of this as adding k plus 1 to the power 3 to both sides of star. And if we do that, we shall have this k plus 1 to the power 3 bigger than 1 over 4 k to the power 4 plus k plus 1 to the power 3. Hope you can see that. Very, very interesting. To observe that, let me take more page. Our page is exhausted once again. More page. All right. Hope it sounds interesting. So please you do me a favor to click the like button if you draw any value from this video. Don't forget to message me if you need a one-to-one online private tutoring or a group tutoring, whichever is the case. I render such services exclusively. So be very free to get across to me for such a service, because I really promise you that you are going to enjoy it, and all the mathematical concepts will be broken down as we shall be speaking one-to-one. All right. So you have the liberty, the considerable freedom to discuss with me on concepts that are confusing, that you are befuddled at. So let's continue with this. Now, over here, we look at the right hand side. Let's try and manipulate the right hand side. Now, observe something. Let's observe something very important. Now, this right hand side can be written as 1 over 4 k to the power 4 plus k plus 1 to the power 3 can be written like that. Can you see that? Then this, you see, if on expansion, we have it as 1 over 4 k to the power 4 plus expanding this, we have k to the power 3 plus 3 combined 1 k squared plus 3 combined 2k plus 3 combined 3, then we have 1 to the power 0, right? Which is this. And this can be further written as 1 over 4 k to the power 4 plus k to the power 3 plus 3k squared plus 3k plus 1. Now, we want to compare this result with the expansion of, let's compare this result over here with the expansion of this. I mean this 1 over 4 k plus 1 to the power 4. Let's do comparison and see which is greater. Now, on expanding, as usual, on expanding this, we know we did the expansion of this in passing. On expanding this, we have k to the power 4 plus, what do we have the other time? Let's just copy the result. Let's go back and see what we had for the expansion of it. Where is it? Where are you? Where are you? Come up. Come up. All right, this is it. K to the power 4 plus 4k to the power 3 plus 6k squared plus 4k plus 1. All right, so let's go and write it down. Then we have 4k to the power 3 plus 6k squared plus 4k plus 1. That is what we had. That is 1, 2, 3, 4, 5. We're very correct, because the terms in the expansion of a binomial are one more than the power of the binomial. That is a fact you should know. So we have this already. So multiplying through by 1 over 4, we have our result as 1 over 4 k to the power 4 plus, then this will become k to the power 3 plus this will become 3 over 2k squared plus this will become honorary k, then plus 1 over 4. Now, if you observe carefully, you see that this expression here is bigger than this expression. Compare the terms, you see. We know that this is the same thing with this. This is the same thing with this. But this is bigger than this. Also, this is bigger than this. And this is bigger than this. So, therefore, we can say that this expression as a whole is bigger than this expression. So, this is our last statement over here. I mean this over here can be continued as follows. So, we can say, we can make this statement. Therefore, let me write this first. I'm feeling tired. All right, I must I must do that for you because I love you guys. I want you guys to draw value from this. From this. It's a very important aspect of maths. So you do yourself the favor to listen up to get a proper grasp of what I'm talking about. All right. So we have this already. So because of that, we can make these statements. One very free. 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot dot plus what do we have there? Let's see again. Is k to the power 3 plus k plus 1 to the power 3. Okay, k to the power 3 in parentheses plus k plus 1 to the power 3. That is bigger than 1 over 4 k to the power 3 plus plus 1 to the power 3. I will find out that this is bigger than 1 over 4 k plus 1 to the power 4. All right? Observe that carefully. Now, from the transitivity property of inequality, this can also be written in summary as 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k to the power 3 plus k plus 1 to the power 3 bigger than 1 over 4 k plus 1 to the power 4. So what are we saying? We are saying this is the same statement originally when we were using n. Do you remember? Let me look for it and show it to you. Here is it again. I think I wrote it somewhere. Look at this s sub 2. Let's see. Okay, look at it here. Yeah, I've discovered it. I mean this. Look at this statement. Can you see this? Look at this. This is the second aspect. You know, this one you are seeing here is equivalent to this you see here. All right. So if you observe the last statement we've made is the same statement as this, but this time around we replace n. It was replaced by k plus 1. N is replaced by k plus 1. Compare carefully. You discover that. Look at it. Observe this statement. You see that it's the same thing with the one we're coming from. So in other words, our supposition, which is star star, here is it again. Our supposition of star star have implied the statement, but this time around using k plus 1. So we can now write the following implication. We can say therefore 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k to the power 3 bigger than 1 over 4 k to the power 4, as implies that we have 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3 plus dot 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 plus k to the power 3 plus k plus 1 to the power 3 bigger than 1 over 4 k plus 1 to the power 4. So what is it saying? Don't forget that this, another way of saying this over here is to say that k is an element of S sub 2. Remember? So that in other words, we are saying that k being an element of S sub 2 has also implied that k plus 1 is an element of S sub 2. And by the axiom of induction, it follows that the statement is true for all positive integers. So we can say therefore n should be in the set S sub 2 for all n that are elements of the set of natural numbers. All right. So we've established that this statement is true. I mean this. Let me go back to where we are coming from. All right. I mean this is true for all positive integers. In other words, S sub 2, which is over here, contains all positive integers. All right. And don't forget to also prove in passing that S sub 1 also contains all positive integer. So that means the union, let me come here. Now, the union of S sub 1 and S sub 2 will give me S sub 1, and that will be also S sub 2. And that is my set of all positive integer. Why this? Because we've proven that the S sub 1 is a set of all positive integer. I will also establish the same fact for S sub 2. In other words, S sub 1 and S sub 2 are the same thing because they are each set of all positive integer, and that is equals to n. So we can now say therefore the statement, what was the statement initially? We had it as, let me look at the statement from the original problem. So this statement is true. I mean this is true. for all positive integer because we broke it into two parts. The first part, we've proven that this part you see here is true for all positive integer. And thereafter, we went over to establish that this other part is also true for the set of all positive integer. That means the entire statement is true for all positive integer, and that completes the proof. So we're done with this particular aspect. Please take your time and to go through it. Let's look at the other parts. This video is taking too long now, but let's look at it together. It's very important you get the idea. Number two, here is the question again. I think I have it here. Let me copy it manually from this material, right? Excuse me. Instead of screen up, let me just get it from here. All right, so we have to establish that 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus dot 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 plus 1 over root n is bigger or equals to root n. Can you see that? We have to prove that. All right. So how do we prove this? Let's go over to the proof of this particular one. So we can say let s sub 0, or we can use any other letter of our choice. Let's use this entity. Let entity be the set of all positive integers for which the statement holds, or you say the proposition hold, right? Because statement is also proposition. I mean, this statement, this is a statement. Hope you are aware of that. This is a statement. So let's this symbol entity be the set of all positive integers for which the statement hold. Now, we want to show that entity is a set of all positive integers. We want to show that. Now, firstly, we go by the steps of mathematical induction. Firstly, observe when n is 1, we have that 1 over root 1 is bigger than or equals to root 1. Do you observe that? That is true. Since it is true, it follows that 1 is an element of the set entity. All right? Because we've already defined entity to be the set of all positive integers for which the statement is true. Now, in this particular case, the statement is true. So that means 1 must be in that set. So the next stage is a supposition stage. We can say, suppose that K is an element of entity. All right? Let's suppose that. So in other words, if we want to, this supposition means that the statement is true for K. That is 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus dot 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 plus 1 over root K is also bigger or equals to root K. That is the meaning of the supposition. That means the statement is true for K. Hope you can get what I'm talking about. Now, let's consider the expression. We can say consider the expression. What is it? 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus dot 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 plus 1 over root k plus 1 over root k plus 1. All right, so let's consider this particular expression and see what will come out from it. I take more page. The page is exhausted already. Now, let me call this star star star, for example, because we shall refer to it. Now, from star star star, we can create this expression from star 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 by adding 1 over root k plus 1 to both sides of the inequality. You observe that? So in that case, we can write 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus dot 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 plus 1 over root k. We can also bring this into parentheses. Then add 1 over root k plus 1 to both sides of that inequality. We shall have this root k plus 1 over root k plus 1. All right, we have these results. Now, what we do want to consider the right hand side of this current inequality. Let's consider the right hand side. Okay, Now, observe something carefully. This, now, look, root k plus 1 over root k plus 1 can be written as, now, when we rationalize this, we can write this as over 1. On rationalizing, we can have root k over 1 times root k over root k. That is, we're rationalizing the numerator. Should we call it rationalize? Okay, let's use that word rationalize. It's not out of place. Plus, because there's a reason why I'm looking at the word rationalize. It's a special word. So we have the result as k over root k plus 1 over root k plus 1. Can you see that? So that is just it. Now, look at this. We want to come. Don't forget that this became this. Okay. Now, note that root k plus 1 on rationalization, using the same trick, you can put it as over 1. We have our result as k plus 1 over root k plus. Hope that is not difficult for you to unravel. It's very easy. All right. It's just rationalizing the numerator. You follow the same process as we did in passing, you get the same results. And this can be written as k over root k plus 1 plus 1 over root k plus 1. Now, we want to compare these results over here with these results over here. All right. I mean this. This. Can you see that? We want to compare this one with this you see here. So let's do the comparison. Now, note, as root k is less than root k plus 1, so 1 over root k is bigger than 1 over root k plus 1, so that we can say that k over root k is also bigger than k over root k plus 1. Did you observe that? So using this comparison, if you observe this one, you will see we have, this, let me use this to illustrate. This, all right? You see we have k over root k plus 1 here. And that's what you are seeing here, all right? We have shown that this is bigger than this. So since that is the case, we mean we are having a lesser result here. Can you see that? Then here we are having a higher result. Look at it. Can you see that? Because we've shown that k over root k is bigger than k over root k plus 1. Now, this is exactly what you are seeing here. Can you see that? So that means in comparison, if we are doing the comparison, this expression you see here should be bigger than this expression you see here. All right? So with that comparison, we can come and write this. This knowledge I'm giving to you is needed in analysis. You need this kind of reasoning process. You need it. You need it. Honestly speaking, you need it. All right? So from this last expression, this expression we're seeing here, or is it this one? Oh, sorry, look at it here. Look at it. Which became, don't forget that this expression here is exactly what you see here. Don't forget that. Don't forget that. So I can replace this with this. All right? Take note of that. Very, very important. So we can now come and make this statement without fear. We can now say, therefore, 1 to the power 3 plus 2 to the power 3 plus dot 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 plus k to the, what do we have? Is it 1? Sorry, it's not 1. 1 over reciprocal of square roots. Therefore, 1 over root 1, plus 1 over root 2 plus 1 over root 3 plus dot 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 plus 1 over root k, this is into parentheses, plus 1 over root k plus 1, which was found to be bigger or equal to, here is it again, root k plus 1 over root k plus 1. I say root k plus 1 over root k plus 1. And this, don't forget, we have shown that this is bigger than this. Here's it again. Look at it here. Can you see that? From the comparison we made. Please take your time to go through this video. It's very, very important. So we can write bigger or equals to root k plus 1. It's not bad we write that, because a disjunction is true if if either of the sub statements is true, then a disjunction is true. It is only false when both of the sub statements are false. We're not doing logic here. If not, I would have explained better. So from the transitivity property of inequality, this can also be written as 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus dot 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 plus 1 over root k bigger or equals to root k plus 1. So what are we saying? We've seen that the assumption of star 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 have implied this latter statement we have here. Can you see that? Oh, it's like I missed something. I omitted. What did I omit? Oh, the parenthesis. Sorry for this. I'll put this first. Brackets, brackets, plus 1 over root k plus 1. I omitted this. Bigger than equals to root k plus 1. So, therefore, we can say star, star, star. I don't want to write that again. It's too long. Star, star, star have implied. Let me call this. Let me call this 1, for example, as implied 1. All right. That is the assumption that K is an element of the set entity implies that K plus 1 is also an element of the set entity. And because of that, by the axiom of induction, we have that therefore n is an element of the set entity for all n that are in this set. That is, in other words, the statement is true for all positive integer. I mean, the original statement is true for all positive integers. So since we have established that, we've proven that the statement is true for all positive integers. So that completes the proof. So we're done with this particular aspect. Let's go over to the last one. Like I'll give you the last one as an exercise. Should I do that? Should I do that? Okay, let me just solve it. Let's just solve it together. The video is too long and it's too lengthy. I want to avoid that by all costs. That is number 3 now. Let me get it from my material here instead of stretching, scrolling up. Now we have 3 to the power 2n plus 1 plus 2 to the power n plus 2. We have to prove that this is divisible by 7. Now let's look at the question carefully. Don't forget the question. You see, for what integer n is this divisible by 7? So in other words, we have to make some statements that these are the integers for which this statement will hold. Thereafter making the statement, we are required to prove that your result is correct. How do we prove it? Now, the statement we are to make should involve the positive integers so that we can apply mathematical induction in the proof process. All right? So we have 3 to the power 2n plus, what is wrong with you? Get out from here. Right. So we have 3 to the power 2n plus 1 plus 2 to the power n plus 2. That is the statement we have to show that it's divisible by 7. So let's make our statement first. How do we make our statement? Let's go down. Now let's look at something. To make a statement, you test for a few values, then you generalize. All right. Then that generalization, you have to prove it that it is indeed correct on the long run. Because the fact that things are correct for a finite set of values does not mean that it will be true for all set of values. So you have to prove that that statement, that generalization is true, indeed true. All right. Let's take case 1. When n is equals to 1, let's see what we have. We have 3 to the power 2 plus 1 plus 2 to the power 1 plus 2, and that will give us 27 plus 8, and that gives us 35. Now, it is true that 7 can divide 35. Please, this symbol means 7 divides 35. This is a symbol taken from number theory. It's different from this, so please take note of this. This is a quotient. While this one means it's a statement read as 7 divides 35. So distinguish carefully between this quotient and these statements. So please don't confuse them. They are different things. All right. So in this case, 7 divides 35. All right. Okay. Now you can test when n is 2. When n is 2, you see that 7 will also divide it. So that we are tempted to say that let's make the statement. Let's make our statement a statement. We can say 7 divides 3 to the power 2n plus 1 plus 2 to the power n plus 2 for all n that comes from the set of positive integer. All right, so we can say that it's not bad, it's not out of place. Let's say that. Now we have to prove this. We have to prove this. It's not just to say it, because it works for few values that do not mean it will work for all. So you have to prove that it will work for all. And we can do that by mathematical induction. All right, okay. So let's look at the proof process. Proof. You can say let A be the set of all positive integers for which 7 we divide the expression 3 to the power is not straight 2n plus 1 plus 2 to the power n plus 2. We can say that. We can see that now. All right. Now, since 7 divides 3 to the power 2 plus 1, as we shown earlier on, 1 plus 2, you know, this expression here is 35. It means that 1 is in the set A. Don't forget how we define A, that A should be the set of all positive integers for which this statement is true. So since when we on testing 7 divide the result here, it means that 1 should be in this set. It's a member of that set, all right? Now let's assume, suppose that K is an element of A. What is the equivalent of this statement? That is 7 divides 3 to the power 2k plus 1 plus 2 to the power k plus 2. So that is, we're supposing that it happens, all right? We're supposing that. We've used a lot of page today. This video is indeed long. Please take your time to go through it. You will draw great value from it. So now let's consider the expression. Consider the expression 2 to the power, sorry, this is 3, not 2. 2 brackets k plus 1 plus 1 plus 2 to the power k plus 1 plus 2. Let's look at this statement. Let's see what will happen. All right. Very, very important. Now, on multiplying this 3 to the power 2k plus 1 plus 1 plus 2 to the power k plus 1 plus 2 can be written as 3 to the power 2k, that is plus 1 plus 2. Please observe what I'm doing. Plus, this can also be written, this other term is 2 to the power k plus 2 plus 1. Now, from indices, this can be equally written as 3 to the power 2 multiplied by 3 to the power 2k plus 1 plus the same thing here. We have 2 multiplied 2 to the power k plus 2. That is, we arrange this expression in light of this supposition. All right, that's what I'm doing. Now, take note, this can be further written as 9. Sorry, this is not 8, this is 9. 3 squared is 9. 9 times 3 to the power 2k plus 1 plus 2 to the power 2 times 2 to the power k plus 2. So we are almost there. We're almost there. We're almost there. Now this here can be broken as 2 times 3 to the power 2k plus 1 plus 7 times 3 to the power 2k plus 1 plus 2. This one here, I think we have 1, 1, 2, 3. We can write this as 2 to the power k plus 2 plus 2 to the power k plus 2. It's not out of place. Can you see that? Observe carefully. Let me see whether there's any error. I think there's no error here. We are in good shape. Yes, we're in good shape. Let's see. Excuse me. I want to ensure that we make no mistake. Oh, wait. What is this? I think yes, 2. Please, yes, 2. Look at it. Look at it here. Can you see that? Yes, 2. So I think I'll put 2 here. That was a mistake we made. I think it's correct now. It's 2k plus 1, 2k plus 1 plus 1 plus 2 to the power k plus 1 plus 2. Right. Okay. Yeah, we are right. We are right. This is 1, sorry. I want to confuse the whole thing again. This is 1. Okay. Yes. I think everything is in order. N plus 2, 2n plus 1. Okay. We are right. We are good to go. We are not, we are very, very good to go. Okay. What next to do? What next to do? What next to do? Ooh, let's take this 2. Let's in fact, this one you see here, you see, write it as, then take it as 2 to the power 3, 2k plus 1 multiply 2 bracket 2 to the power. Let's write it like this. This will be profitable. To be very, very profitable. 2k plus 1. Okay. Now, if you observe carefully, what is common here? 2 is common, so we can bring right as 2 bracket 3 to the power k plus 1 plus 2 to the power k plus 2. Can you see that? Then we're left with 7, 3 to the power 2k plus 1. Now, from this our assumption stage, this stage shows that 7 divides 3 to the power 2k plus 1 plus 2 to the power k plus 2. Since that is the case, it means that 7 divides this. All right. So in other words, this term is divisible by 7. And of course, this one here is clearly divisible by 7. So we can write that since 7 divides 3 to the power k plus 1 plus 2 to the power k, this is 2, please, 2k, k plus 2, since that happens, and okay, and 7 also divides 7 multiplied 3 to the power 2k plus 1, it follows that 7 divides this entire expression. Do you agree with that? This entire expression. 7 divides it. That is, in other words, 7 divides this. Hope you get what I'm trying to say. So we can say, therefore, 7 divides, what is the expression again over there? 2 bracket k plus 1 plus 1. 3 raised power 2 bracket k plus 1 plus 1 plus 2 to the power k plus 1 plus 2. It means that 7 divides this expression. So what are we gathering from this? The assumption that 7 divides this, which is the assumption stage, has implied that 7 also divides this. In other words, the assumption that k is an element of what was the set we are dealing with? It's not A. We're dealing with set what? Set A. So the assumption that k is an element of set A has implied that k plus 1 is also an element of set A, which means that n is an element of A for all n that comes from a set of natural numbers. So we've shown that 7 can divide the expression which is above here. I mean this expression. I mean this. Okay, wait, let me. Okay. Yeah. I mean this expression. All right, 7 can divide it for every n. This expression is divisible by 7 for all positive integers. So we've established that, and this completes the proof. So this is just all about mathematical induction. It's very easy. Just three step to go. All right, the first step, you show that this expression is true for when n is 1. When the number is 1, of course, it's not necessarily 1. It can be 2. It can be 3. After showing that it's true for any of this number, you suppose that it is true for an arbitrary constant integer, positive integer k. Then from that supposition, you show that that implies that it is true for a positive integer k plus 1. If you can do that, you've established that It is true for all positive integers. So that is the process behind mathematical induction. It's not difficult at all. So you take your time to go through this video, go through it once, twice, thrice. As it's very long. So take your time to go through it so that you can get what I'm talking about. If you spend time with this, you must surely get the entire concept. So thank you very much for paying attention. I really appreciate you all. We have a good day till we meet in other video. Don't forget that I render online tutoring service, math tutoring service. So if you are in need of this service, be very free to get across to me as you will draw great value from such a service. So thank you very much. I really appreciate you all. Do have a blessed day.